Right, wonderful. So, hope you enjoyed lunch, and after lunch, let's do some exercise to get our bloods going. So, I'll begin by explaining exactly what we've built, how it all assembles together, and then we will tackle all the main components in the system. So, going from the code on the watch, to the code on the mobile, to the Akka cluster, the database that stores all the events, and the machine learning that happens in Spark, or rather, the improvements to the model that happen in Spark. Now, the motivation for building this application was the fact that I really didn't want to keep a log of exercises in the gym. I was too lazy. So I wanted to build something where I could just go to the gym and get on with stuff. And it would do all the work for me. So it would classify everything that I did, depending on how I moved. So I bought a watch, bought a new phone, and I bought a whole bunch of other stuff that I could play with. And the result is this entire code base, and we'll walk you through every component, and hopefully you'll be able to get an appreciation, perhaps, of all the technologies and all the languages involved that you saw in this morning's keynote. So let's just get on with it. So suppose you want to write an app that looks just like this one. Well, here's what would be involved.
Yeah, so as you can see, we use plenty of different languages. For example, C++ and C for lower level development on the devices. We use Scala for backend development. We use R and MATLAB for mathematics and machine learning experiments. The dominant language here seems to be C++, but it's caused by inclusion of some third-party libraries. So the most used languages should actually be Swift and Scala, probably. This is the open source version of our project. So if you're interested, feel free to have a look. All the code that we will be describing today is available in GitHub.
Yeah. So the only thing that's missing is an Android. We'll be happy to take a pull request. But otherwise, it's all there. So let's begin with the smallest of our computers, a Pebble. Does anyone have one? Oh, you have to buy one. They're really cool. They're really cheap. And they are really fun to program with. In fact, here's how we treat the Pebble Watch. As far as we're concerned, it's just an accelerometer with Bluetooth Low Energy hardware. That allows us to send the values that we measure, the acceleration values that we measure, through to the mobile phone. Now, you know, in a drawing like that, that sounds and looks really easy. And here are the kinds of numbers that the watch spits out. It measures the acceleration in centimeters per second square, milli-Gs in normal human speak. It's a little bit crazy. The reason for that is it doesn't have any floating point numbers. All that you get on a Pebble are integers, signed 16-bit integers. In fact, in a Pebble, you get about 20 kilobytes of memory for your code and the data structures that you allocate. So we really don't have that much space to play with in our programs. And the data packet that we send to the mobile can only be 625 bytes long at a time. So we can record 625 bytes worth of stuff and then send it to the mobile in a packet over Bluetooth Low Energy, which comes with all sorts of interesting timeouts and error conditions that we have to deal with. As you might guess, if we drop a packet, that means we've lost a second and a bit of data, and that disrupts the entire classification. So we really have to be extra careful to make sure we send everything in a timely manner. Here's another view of the very same chart that you saw. It's just a matrix of 3 numbers, x, y, and z acceleration, or rather gravity. So if I hold the watch, one of the axes will be 1,000 for 1G, and as I move it up, that changes. So nothing unusual here. So we would like to write these sane Pebble applications. They're responsive and resilient, all reactive. We have no operating system on a Pebble. So the only way to do it is to interact with the watchdog timer. And essentially it means that if you don't reset the watchdog timer, the hardware of the watch replaces your program with its firmware. And it says, your app has crashed, and it's gone. So great. It's resilient and responsive, because if we wait too long, it will be removed from memory. But the key thing is, throughout all this stuff, it's important to write the core components in plain old C with tests in C++. It has to be tested. It's normal software engineering. The only trouble with Pebble is that it doesn't really come, its SDK doesn't really come with support for tests. And so we wrote our own. So we have a mock framework that allows us to write normal Pebble code in C, build it in CMake. So this is a standard C, C++ toolchain. CMake, whole bunch of code. The core, of course, has to be in C because it needs to be compiled for the Pebble SDK. But the tests, that's plain old C++ and gtest, which incidentally explains the massive C++ code base. And then we have just a tiny fraction of the code that's specific to Pebble, the thing that just wraps the components, provides the shell for the user interface that is built using the Pebble toolkit and installed, again, using the same Pebble SDK. So in code, just to spring some names into it, the A functions beginning with AD deal with the accelerometer data, and the functions beginning with AM deal with what Pebble SDK calls application messages. That's the Bluetooth communication. And so I have a quiz, in fact. How many bytes in the 3D data structure? Any guesses? 40 is good, right? But it's 40 bits. Remember, we need to squeeze as much as we can. So these are 13-bit signed integers, big endians. But that's 39 bits, which is a bit of a silly number. So we need one more bit, which we call valid. It's another indication that the watch can say, look, my sensors are broken. This will be 0. So in any case, 5 bytes for a header, 5 bytes for each packet, which means that we can send 1.2 seconds of data in each Bluetooth packet. So that's how much time lag we have. Record 1.2 seconds, that's what goes to the mobile. Now, the API, unfortunately, C. There is no object-oriented. Type safety goes out of the window, right? Void, star, and we can knock ourselves out. In any case, we implement these. Well, we send the structure, we implement the functions. Again, if you're interested in using the Pebble SDK, this is what a Pebble SDK code would look like. It's a normal, fairly sane C API with a cross-compiler for Windows and Linux and OS X. So it's not a problem. The cool thing is, the thing that you should always do is to test it. Now, using our mock Pebble framework, which is, again, open source, available on GitHub, it's perfectly reasonable to write a gtest test and make assertions. So we have this mock Pebble, and I can have the acceleration service, and I can push to it the mock data, and I can assert that what it encoded is what I expect. So normal code, right? That's built in CMake, that you can run in your Jenkins or whatever CI pipeline you have, and then just have a tiny fraction of it that deals with the Pebble code. In fact, application messages, right? This deals with the Bluetooth stuff. Tested in a very much the same way. So the app message register open and outbox failed, that's the Pebble SDK. And that's how you would interact with it. It's actually reasonably well documented with good IDE. Has anyone tried CLion, by the way? No? Do try it. I mean, Xcode is awful, but CLion is cool. It eats batteries, but other than that, it's really good. In any case, you can write good, sane C program, and then only delegate the tiny stuff to the Pebble-specific code. So if I abstract away all this core and call core as my shared object, a library, then it gets used here, AM stop and AD stop, when I quit the Pebble application, and AD start given an AM start when I start the Pebble application. That's few more lines of code. That's my main code of the Pebble app. That's the only code that is built using, or that's built outside of our CI and CD. That's the Pebble SDK running it. We cannot actually test it on our CI and CD server. It has to be installed and executed on the hardware. Well, in any case, this completes the tiniest of our computers. That's the Pebble. It receives data, uses the accelerometer, and it interacts with the Bluetooth, sends quote-unquote real-time communication to the phone using, again, Bluetooth low energy, 1.2 seconds of data at a time. So let's talk about a bigger computer. Actually, this is a really funky computer, a mobile. Now, in our world, it turned out that recording exercise from just one sensor was really insufficient. So you can think, okay, it's a big exercise, I can do this. Great. But there are plenty of other exercises that I can do where my hand doesn't move at all. So I can be doing dips and my hand just doesn't move, and yet I'm exercising. So we thought, that's a bit of a problem. It turns out that to do proper classification of exercise, it's necessary to fuse data from multiple sensors. And so what I can have is an accelerometer on my wrist in a watch. I can have a heart rate monitor. And the phone itself is actually a rich sensor. So it can give me acceleration, can give me rotation. And so the simplest case, the simplest thing we say to our users, say, look, just keep your phone in your pocket, keep your watch on the wrist, and that gives you a really good approximation of all the exercises that you're doing. There are now 2 sensors on you that are recording different positions on the body. The more sensors you have, of course, the more accurate we can be. Nevertheless, the job for the mobile phone is to connect to all these devices, a heart rate monitor, if you like, and a Pebble, and to collect data from itself. And then to somehow merge the 3 different streams, make sure that the time units align. So at time 0, it really is time 0 on the watch, time 0 on the heart rate monitor, and time 0 on the phone. And at time 1, it all adds up and aligns. Now, the slight problem with that is the sensors and the Bluetooth, and it's all a bit of a mess. So the sensors like to leave gaps in the data. They're not real-time operating systems, and the phone isn't a real-time operating system. So we have every now and again, there's a few milliseconds of a gap. Well, that's okay. Humans are humans. We don't really move that far in a millisecond. But sometimes there's a bigger gap in the stream, in the data that we receive from the devices. And if you add to it the data from the phone, if we sent this, well, it would be a bit of a problem. So what we need to do on the phone is to align the data and pad the known zeros. So the software on the phone actually moves away from wall time, the actual time measured on the clock on the wall, to some sort of synthetic time, block 1, followed by block 2, block 3, block 4, and they're all of exactly the same length, which makes our further classification pipeline a lot easier, because this classification pipeline, it doesn't have to worry about time. It just sees, okay, block 1 was this, block 2 was this other thing. All that it has to do is to check that block 2 isn't preceding block 1, which is relatively simple. Now, sane mobile applications, it's the same stuff, right? So responsive and resilient, now these are actual real-time, not real-time, these are actual real operating systems. And I'm going to show you a bit of code in Swift. Now, if anyone's doing iOS development, you want to have dependency management with Cocoa Pods. Swift for the better programming sanity of programming language. We used Alamofire to do our networking. And because at heart we're actually Scala developers, we thought we would use Swift-Z. Has anyone tried Scala-Z? Excellent. Excellent. Right. So Swift-Z will be no surprise. To every one of you, Swift-Z will be a pleasant surprise. Right. So great stuff that Swift gave us is sane data structures. So in our case, a user is a struct. So we use the structs as a bit of a namespacing tool in Swift. And we have a public profile, which has a first name, last name, weight, and age, and a couple of helper functions. So we can say, okay, if someone wants to start with an empty public profile, we say user.publicprofile.empty, which gives us this packaged up, prepackaged empty public profile. Now, we also then wrote extensions that deal with JSON marshalling and unmarshalling. Now, this isn't probably the real code, but just to give you an idea, an extension on the public profile with an instance method marshal that takes that actual value of user profile and spits out a map that can be turned into a JSON and a thing that can go in the reverse direction. So given this JSON object, we can pull out the fields that we're interested in. We then add to it URL. So this app now needs to talk to the server, and it needs to talk to its RESTful API. We really didn't want to sprinkle the URLs throughout our system. In fact, we wanted to lock it down as much as possible. And you might have seen this pattern called type-safe URLs, in that the mover server URLs, it's just an enum that implements mover server requests convertible protocol, and the case classes, the actual values of the enums, represent the things that will be translated into URLs. They can have parameters, so I can have a user ID, or I can perhaps have a session ID in the second case. And I can then say, okay, well, what is, given that I'm holding a user get public profile value, what is the URL for it? I can do a pattern match. Don't worry about the closing braces. We're not going all Lisp on you. It's just formatting. So this is a nice pattern that we found. So the URLs are defined only in one place. And the only thing that our users, or rather the programmers, are allowed to interact with are the values from this enum. So it's a nice way to package it up. Now, mover server. Remember, responsive, resilient, so it wants to be asynchronous, it wants to be non-blocking. Now, making requests in a non-blocking way is usually a pain. Now, let's have a look at this. So there's the usual singleton song and dance that we have to do in Swift. And then, let's take a look at user get public profile. It takes a user ID as a parameter, nothing too unusual. And then it takes this second thing, a function from a result of user public profile to void. And the function itself returns a void immediately. So what does that actually mean? Well, if I call it, I get a result immediately back. I already hold a void. And then at some point in the future, when the request has finished, this f will get called. And f will receive a value of type result of user public profile. Now, what is this result? Result is an enum that has two possible values. Either it's a success, if you like, a value, so it has worked, and I am now holding a user public profile, or I'm holding an error. Now, I have to do that because, remember, I'm asynchronous. Exceptions are long gone. They may have happened on another thread. So at this point, I need to decide. I need to hold the entirety of the result. But that's kind of complicated. Then I want to somehow do something interesting with it. And one of the useful things I can do with it is to have this function called catamorphism in category theory. Now, scary thing, doesn't really matter. Think of it as breaking down of a shape. That's what that means. Now, the shape, the thing that I'm breaking down is a result. So I need two hammers to break it down. One hammer to break down the left thing, the error, and another hammer to break down the success. In other words, what do I do when there's an error? Or what do I do when there's a success? And both of these operations need to give me the same type. And so in Swift speak, the kata of u as a type parameter, function to do a thing on the left, function to do something on the right. Here's how it's actually used. I think this is actually really pleasant. So on a home controller, which is a UE view controller and a whole bunch of other protocols and classes, let's say I want to display a public profile. So move a server, shared instance, get the singleton, user get public profile, that's the method call. I give the first parameter, so far so good. And then as the second parameter, it's the function from result of user public profile to void. That's the $0, and then if it's error, I want to show error. If it's success, I want to show result. And this is actually pleasant enough code. It's asynchronous, it's non-blocking, and yet it's sane from the point of view of writing the code. So, few final things. How do we talk to these devices? Well, we named them, so these guys are instances of device. We talk to a particular connection to the device as a device session. The phone has a multi-device session which combines the different data from the different device sessions, combines it into a sensor data group by padding the data and making sure that it all aligns, and sends the data off to the mover server, which is a whole bunch of Scala code. Just to give you an idea about a Pebble session, again, if you want to use the Pebble SDK on iOS, it's just as easy as calling, getting an instance of Pebble Watch and then calling the appropriate methods. Oh, yes, I did have a question. Does anyone spot a reference to Doctor Who? No? one of our fancy constants. So it's not the 000 dead, it's face of bow. But anyway, we are geeks, completely and utterly. Interestingly also, it is necessary to construct an instance of ns number of uint32 because this code needs to be compatible on the 32-bit ARM code and a 64-bit ARM code. If I just said face of bow, then it fails on the 32-bit compiler because face of bow would now be a signed number of negative something. So if I want to make sure these are unsigned numbers, I have to create an instance of ns number, specify that it's actually a uint32. So heads up if you're doing for programming for iOS 6 and iPhone 6s, I mean iOS 8 and iPhone 6s, and I don't know, iPods, then you might come across these interesting problems. In any case, accelerometer data received. These are the data that are received. Same structure, right? Now, at this point, it's quite comfortable. It is actually possible to use plain old C structs in Swift unless they have these bit patterns. So if I have 13 bits, 13 bits, 13 bits, then the Swift compiler will just pretend that this structure doesn't exist. Yay. So we have to go back to C, plain old C, and just juggle the memory around. We can call these C functions from Swift without a problem. So one more little annoying thing if you're doing iOS programming. And finally, don't worry, I don't actually expect anyone to possibly read this code. In any case, as the data arrive from multiple devices, they are combined, padded, timelined, and then finally sent off to the server here. x.submit data is the golden ticket. Take the data, align, pad, construct these timeless, if you like, packets, send it off to the server for processing. So in other words, this should all make complete sense. Or rather, when you clone the code base and open the hundreds and thousands of lines of code of Swift, this might be making some sense. Okay, great. So we have devices, combine the data from the sensors on the phone, and we send it off to this Akka cluster to analyze. So this is where another component of our, if you like, machine learning pipeline comes in. We go from multiple sensors, and then now in real time, we have to do this processing in an Akka cluster. So here's what it looks like. Devices on the left, the Akka cluster does three main things. It maintains user profiles, if you like. It also maintains exercise programs and suggestions. So this is where you open the app, say, what might I do today? And it says, well, you really should do this exercise at this intensity. And then, of course, it receives the data and processes them. The result of the classification is actually not just the name of the exercise. It's far richer. So in this example, I've done 9 of these bicep curls. And the result of the analysis at this point is do one more. The analysis is tuned for me as a user for this particular exercise session, for this particular intensity. So we go to really a lot of detail. What we're hoping to achieve in future versions is to be able to have some sort of physiotherapy interface that says, do this movement. So the patients will have been trained to do this movement. And then they can do it on their own. And the result isn't, oh, yes, you've done movement A. The result is, okay, well, a little bit harder on A, or hold the arm up a little more, or something like that. So it's all rather exciting. Here's what it looks like inside. There'll be quite a few Akka talks coming up throughout the day, so if anyone's interested, I encourage you to come along and try. It is a cluster. It is really, truly a reactive system. It is elastic. Can add more nodes if we find that we are lacking processing power. We distribute the entire domain. So the domain of our application is all the users, all their profiles, all their exercises. Now, clearly, this wouldn't fit inside a single JVM. So it needs to live across multiple different JVMs. It needs to be distributed. And the components, if you like, the reason why there's a line is I like to think of these things as distributed domain at the top. So these are the, call it user exercises, and user service and the exercise service. And the thing at the bottom, which I like to call distributed computation. It's the roughly similar story. We just say that the thing that we are doing, the computation, is too complicated, too big to fit inside a single JVM, so it needs to be spread across multiple JVMs. And they're connected to those two rubbish bins, really. No, it's a journal and a snapshot. It's a database where all the events go. Martin is going to mention something about event sourcing. There's a whole talk coming up after this one, in this room, that deals with the details of event sourcing. In any case, we have simple structure, load balancer at the top, couple of nodes, each with their RESTful API that deal with the data that's coming in, and they generate events. These events end up in journal, and we can construct the state of the system by replaying all these events. So, nearly there. In terms of profile service and exercise service, they follow the same shape. So at the top, there's a Spray service. So Spray is this HTTP API that's suitable for Akka. Oh, well, I'm biased, so I'll say it looks really pretty and it's quite readable, but then again, you'll be the judge. We'll show you some code. Talks to a couple of intermediate actors and a few more actors. So in case of the user profile processor receives all the requests, validates them, and then we have an instance of user profile for each individual user. So this is where the sharding, clustering and sharding comes in. We have one instance of this actor per every user, ever in our system. And they are spread across all the nodes in our system. It's a similar story for the exercise. The exercise service, that's the API, that's the thing that translates the HTTP requests into messages that the underlying actors can understand. And now the user exercises processor deals with the requests and it generates events. Events end up in the journal, potentially in the snapshot, and then we have these things that are in pale blue, user exercises sessions, user exercises session, and user exercises statistics. They are what's called views. So these are also actors, and they get to see all the events that the processor has generated. They don't get to create new ones. They just get delivered these events, and they play back the events and compute their state. And so when you say, okay, what exercises have I done, or has this particular user done? The answer is, well, my state now, because there's an instance of user exercises processor for each user. Well, how does this user exercises sessions know which state it is in? Well, by replaying all the events, by receiving everything ever in history that the user has done. So we have a complete, if you like, audit trail of everything that has happened. All right, in code.
Yeah, so this is implemented in Akka using Scala programming language. Akka is essentially a framework that allows you to simply build concurrent and then distributed systems. This is the REST API Jan was talking about. You can see the Spray gives you a very nice DSL to build the REST resources. So you can have user ID /check, for example. These actors, there's a notion of we pass those actors to this REST API as actor refs, and this REST API can send messages directly to those actors, and they process it. We'll have a look at those actors. If you don't know Scala or Akka, it does not really matter. It's quite simple, and you will see that it quite clearly resembles the images Jan was explaining before. So this is user profile processor. We have one of those actors per node. This is persistent actor, so it has some kind of state, and this state can be persisted into database. It has to override two methods: receive recover and receive command. Receive command defines behavior of this actor, how it responds to messages that it receives during normal runtime, and receive recover that defines behavior. What happens when we receive messages that happen during recovery? So when this actor dies, or when the node on which this actor lives dies. First thing that can happen is that this actor receives user register message. It checks, it does some validation. It checks if that email already exists. If it knows it, it stores it in its. It has known accounts in its private var, in its private state.
So this is where I've typed it in as user. I've typed it in using the mobile app. I said, here's my username, here's my password, and I said submit. It got here, and I got back username already taken.
Yeah, so if the username already exists, we all immediately respond to sender. Sender in this case is the REST API. We respond with left, which by convention is the left part of the disjunction, which means error. So it is immediately translated in the REST API to HTTP status, in this case 400 or something. If the validation passes, if the email does not yet exist in our local collection, in our local state, we persist this event. We send the event, we forward it to user profile actor, and we mutate our internal state. So this actor adds the new account into its internal state, into the collection of accounts it already knows. And again, it responds to sender, to the REST API, in this case with write, and write is translated to 200, so the user that uses his mobile device immediately receives a 200 HTTP response. As I mentioned, we have one of those actors per node, which works perfectly if we have only one node. But if we want to scale to multiple nodes, if we want to make the system distributed, which we do, we need to somehow synchronize the local account collections between actors. I will not talk about the CAP theorem and about how to do it, but there are some considerations that need to be made between consistency, availability, and partition tolerance of the system, so we need to do those considerations. Another actor we have is user profile. User profile again extends persistent actor, so it needs to again override the same methods, receive command and receive recover. The difference in this actor is that it actually has multiple states, so you can see it starts at not registered. And when it is not registered, it expects some kind of messages. So it expects account message, and when it receives account message, so it starts as a blank template. It does not have any profile. And we have one of those actors per user. So when it starts, it does not have any profile. It receives the profile as a message. It mutates its internal state. It saves a snapshot, and it changes its behavior to registered. So from now on, it is registered. It starts replying to different kind of messages. So in this example, for example, when it receives a get account message, it replies to sender with its internal state, which is the account. It's stored in memory, so the response is immediate. User exercise processor is another actor. Again, you can see it follows very similar pattern. But in this case, this actor actually contains a different part of the domain. So this actor takes care of exercise session of a user. So it starts as not exercising, and when the user starts exercising, so when the user goes to a gym and actually starts lifting weights, this actor changes its state to exercising. And when it's exercising, it expects those messages that it has defined the behavior to. When it receives exercise data process multi-packet, which is the data from sensors, it just forwards it to classifier and asks it to classify the messages. And the responses from the classifier can be, I know what this exercise is, I classified it, or it was no movement, it was no exercise. And this actor only does one thing, it persists it. But as Jan mentioned, there's a notion of a persistent view, and this view listens on this listens for those messages that are persisted, and it builds, it pre-computes its internal state, so it has defined answers to certain queries. So for example, there's a user statistics view. It expects messages of type classified exercise, and it pre-computes answers to queries about user exercises. So we can then ask this view, what exercises did this user do last week? And this view has pre-computed answer to this question in memory, and it can immediately answer.
Okay, so here's the exciting part. What you saw on the previous slide was this magical classification.classify. And Martin said, oh, and this thing just does it. Well, in fact, here's what it does. There are two main components. First, on the left, we have some sort of signal processing where we have to tidy up the signals, really take care of, spot the paddings that the mobile app has added. And then the result of that is some sort of straw man, really, or wire man, if you like, with the right values attached to the right area. So there's a accelerometer data from the wrist and rotation data from the waist and the heart rate data. That's what goes into the machine learning pipeline. Now, that's the more complicated bit. Here's what it does. It splits the entire request. So first, on the top, we have to remember who sent us the request. Because remember, we have to reply back to whoever called us with fully classified exercise or no movement or no exercise. So that's easy. We don't do anything with it. We just pull out the sender and leave it. On the bottom is where the actual real deal is happening. Now, what we do is we take the values, which we call SensorNet, and we take column slices of the data. So we don't process the entire 1.24 seconds at a time. We take smaller snapshots. And in those smaller areas, we try to identify the features. We call them facts, if you like. And that's the job of the first component on the left, which we call workflow. It produces a thing called bind to sensor. So we bind facts to sensors. Just so we don't get into too much detail, in this case, the sensor can be the pink area and the next pink area next to it and the light blue and the red area in the bind to sensors value. So we've thrown away the signals. We no longer have these matrices of numbers. We have these pink, and blue and red. Now, we feed those pink, blue, and red to a couple of queries that we have. Now, the queries form part of our exercise model. And for every query, and we'll get to see what that is, we feed it to a query evaluator. So we need to decide whether it's true or false. Then we feed it to an exercise decider. Because remember, the outcome isn't just this is exercise blah. The outcome is do one more of exercise blah. Try harder with exercise blah. How about heavier weight in exercise blah? So that's the job for the exercise model. The result is, if we're lucky, classified exercise that we join together with the sender. And by joining, I mean we reply to the sender. Here's the result. Here's what we have. OK. So this guy, a couple of different approaches. The one that you get in the open source version is a support vector machine trained to recognize simple gestures. There's a whole bunch of R code that you can collect the data, and then there's an interactive R program that you can use to label the data. And it spits out a libSVM model parameters that we load here into a support vector machine that we then use as a typical binary classifier. There's some threshold, and if the data matches the SVM trained data by above that threshold, we say, yes, this is a result true. OK, that gives us the facts. We feed those facts to these queries. Now, to give you an idea of what this query might be, a query might be at least one pink and diamond blue, which means followed by at some time in the future blue. We have used LTL, so linear time logic, to implement that. We have actually internally used the CVC4 theorem prover to evaluate these queries. Now that's all implemented in C++. We've taken the API, so we haven't actually done the hard work. In any case, the queries look like this. So for this particular exercise, we're looking for at least one pink, followed by at some point in the future blue, or red, as it's done. Now, if this query evaluates to a stable value, meaning we know it's true, or we know it's false, we feed it to the exercise decider, and the exercise decider is a state machine that says, look, if I begin, so in essence, if I begin doing this, 1, then it's very likely that as my user, another one of these movements will follow. In fact, it's very likely that 8 of these will follow. And when I've done the 10th, it's very likely that no movement will follow. So these are the different weights on the state transitions. And the outcome when we reach a terminal state in our state machine is the classified exercise. And that's what we feed back to the sender. So hopefully, this gives you a rough idea of what this Akka cluster does. So we've gone from sensors, fused the data, sent the sensor data, we had a profile information distributed across the cluster, we have the exercises distributed through the cluster, and we run this machine learning and classification pipeline on the data. The outcome is stored in a journal. Remember, these are the events that end up in the journal. And we can read them from the journal, which is terribly exciting because
so
we do analysis.
we use Apache Spark for this. Apache Spark is a distributed, fault-tolerant, and scalable solution for big data processing. In our architecture, we use a common interface between Akka and Spark, which is Cassandra database that stores the journal of events. Akka has this concept, as we mentioned, of persistent views, and those views can answer some queries to some expected queries, some pre-computed questions. And Cassandra can also answer queries. It's a database, so we can query it. But it's mostly an operational database, so it can handle large amounts of writes and reads. But the querying model it provides is not as flexible, and that's exactly why we use Apache Spark. We can use it for more complex iterative analytics over the data. So we use it, for example, for suggestions, for recommendations. We can group users by some similarity attributes. We can train our machine learning models and so on. So we use the concept of event sourcing. So each event that goes through Akka is stored to a journal. Well, we won't go into detail on this because Duncan, in his presentation in this room, in his next presentation, will talk about this more. But it actually means that we have the whole history of events that ever happened in the system available. This gives us a lot of flexibility for our analytics. And this is exactly what we use Spark for. It can handle those large amounts of data, it can scale, so we can run all those analytics as we want. Both Spark and Cassandra are distributed systems, so they live in a cluster. They can live in different clusters or in the same cluster. They can be on the same nodes or not. We can also have multiple Cassandra databases, and we can use asynchronous replication between them. But the important thing here is that they actually work very well together. Spark has this Cassandra connector, and this connector knows where the data physically live in Cassandra. So when we are doing query using Spark, it knows where the data are, so it can optimize this query. It can optimize the data locality to make the query as fast as possible. Another important thing here is that Spark is a distributed system, it's a long-running cluster. So when you want to run a job in Spark, you don't just run Spark. You have a long-running cluster, and you just submit a job to that Spark cluster. This job is then automatically distributed to all the nodes it has to optimize, to utilize the resources you have available to utilize the whole cluster. When I say submit a job to a cluster, there are multiple ways to do it in Spark. One of them is to use a submit script, but we wanted something more flexible, so we built our own framework how to do this. This again uses Akka. This is an actor, and this actor receives a message to batch job submit. And in this case, we submit a job, a suggestions job to the cluster. Suggestion job, we'll talk about this a bit more later. It's a job that suggests intensity of next exercise to the user. This is a typical machine learning pipeline and a typical job we use in our Spark cluster. So we receive some data, and the data are split into two parts, testing and training data. Then we do some pre-processing on the data. We do some normalization on the data, we do some dimensionality reduction, we do some feature extraction, and then we use the training dataset to train a model and testing dataset to test a model to receive some kind of error. We know how the model performed. Then we can try using different models. So on this example, you can see the deep neural networks, support vector machines, or decision trees. And each of those models has a number of parameters. So we can, again, try to optimize those parameters to achieve the best possible result. There are multiple things we can do. We can try to optimize those models, their parameters. We can try to optimize the pre-processing pipeline and the input data. And we may want to do this for each user separately, and we may want to do this with large amounts of data. These are iterative algorithms, so this is really computationally expensive, or maybe computationally expensive, but this is exactly the use case why we need Spark for. Spark has a machine learning library, And it allows us to define those machine learning pipelines quite nicely. This is an example. We define some kind of user filter, some normalizer, then some feature extractor, and then some machine learning model. In this case, it's a simple linear regression.
By linear regression, of course, we're hoping that if you start with intensity 1, and tomorrow you do 2, then the day after you'll do 3, and you will improve forever onwards.
Yeah, so it actually makes perfect sense for intensity. This is how one of the stages in the machine learning pipeline may look like. Notice the transform function. We actually have the whole data set as input, and we can do all the operations that Spark provides us on it. So we can do some maps. In this case, we use sliding window. So we use n previous exercise intensities as features and the current exercise intensity as a label. And we use those data to train our models. As you may have noticed, we may want to use the very same pipeline for multiple stages in our machine learning. So we use it to train the model, to test the model, and then in real life use. So it is very nice that Spark actually gives us a way how to define this machine learning pipeline quite nicely. We create a new pipeline, we set stages, we set them in certain order. And then for each eligible user, for each user that is eligible for this job, for the suggestions job, we first fit the pipeline to the data, which gives us the machine learning model, the trained model. And then we prepare test data using the very same pipeline. And in the end, we use the model to create predictions of future intensities. And the result may look like this. The blue dots are previous exercise intensities, and the red line is a fitted linear regression. If you notice, the red line actually continues more to the right, past the last known intensity. And this is where we expect the next intensity to be. So our prediction will rely on that red line.
All right. So we have a demo. Recorded. I'm not completely mad. So here's what happens. So I type in my username and password. Suppose I want to register. That goes through our Swift tab, through our responsive library, to the user exercises, to the user profile processor. Then I can fill in my profile. I can need to specify where I keep my devices, that the phone is here, that the watch is on my wrist. I submit the job that has submitted the request. It has gone to the user exercises, to the user profile. I click on one of the exercises, remember the result of the machine learning analysis. And now I'm actually doing exercises. This is where I, behind the screen, wave my arm like a lunatic. Anyway, data from the sensors is arriving. We're padding them up, sending the data to the sensor that hits the user exercises processor. The user exercises processor decodes it, sends it through the classification pipeline, persists the events that the views see. Now, when I choose to stop the exercise and look at the result of the view is simply a playback of all the events that I've done, all the classified exercises, and take my word for it. That's sort of what I've been trying to do. Lab conditions, I can do what I like. And also it's video. So this all worked really, really well.
Yeah, so in conclusion, we implemented all this. We used the technologies and the languages we just described. We started using it in production with some real users, with some trained machine learning models. And Jan will tell you how that actually went.
I have some summary slides somewhere. Oh yeah, it was a disaster, right? Nothing worked. We gave it to 100 users in the gym, and they couldn't use it, right? So, first problem. The data loss from the sensors was actually really significant, so we couldn't classify anything. Because of our naive padding, we had all sorts of zeros in the data. That didn't help. Because we were sending all the data, all the heavy classification was done on the server, we had to make a request every 1.24 seconds. The timeout on that request had to be at most 1.24 seconds. Has anyone tried 3G? Right. So it didn't work. We sent a lot of data. Now you think, oh, well, how hard can it be? That was about, a kilobyte per second we were sending, except we had 100 users exercising every day. And all of a sudden we were thinking, dear, this is, 15 megabytes for every user. We have 100 users, that's every day. And I didn't want to spend money on AWS. But that's by the by. We were sending too much stuff.
Yeah, another issue connected to the bad feedback from users is that we did not know if our machine learning, if our classification was correct or not. So we did not have any feedback on our models. We couldn't improve the user's experience.
So yes, as a result, it was just meh. It was disappointing. It was terrible. Right. So what do we do instead? We have to have a better sensor. We have to deal with sensors differently. We have to have a shorter experiment life cycle. Or cycle when we try a new model, try a new query. How quickly can we go from a new model to actually working software? And we need to shuffle the computation around. So we gave it this grand name, distributed Lambda architecture with feedback. You're more than welcome to it. But I will show you in slides what it actually is and in code.
Yeah, so if you work with big data, you probably know this. This is called Lambda architecture. All the data is sent to the green and red boxes. The green box is called the speed layer. The speed layer processes data in real time. It pre-computes some views. It processes the data. And the red box is called a batch layer. And this batch layer does more complex queries, more complex computations. It usually is not in real time, so it lags behind the speed layer. And then both of them, the data, the pre-computed views are sent to a so-called serving layer, and this serving layer merges the pre-computed queries of both those layers. So this is the architecture. You've seen this slide before. This is architecture of our solution, and it actually fits very nicely to this Lambda architecture. The green box, in our case, is Akka cluster. This Akka cluster does some signal pre-processing. In this case, it's fast Fourier transformation, then some pre-processing on the time series, such as symbolic aggregate approximation in this case, and then it does the actual classification of the exercise. And the red box, in our case, is Apache Spark, and it does the more complex queries. It trains the model, and it tries to figure out the best model for each user or for the use case. This is the architecture we had, and it did not work very well.
Yes, and that's what we have now. This works wonderfully. Terms and conditions applying. In any case, we've split the speed layer, if you notice. So we have a portion of the speed layer running on the mobiles. These are completely different computers on a completely different networks, different quality of service, different everything. So we have actually shifted a lot of the computation over to the mobiles. And second thing, of course, users get to pay for their battery life, which is great. I don't have to compute it on AWS. Only some data gets sent to our server. And by only some data, we mean the confirmed positive classifications and confirmed negative. So what we get on the server, which allows us to improve the models.
Yeah, so another improvement from the previous architecture is that now we have feedback between the two layers. So we have feedback from user. We know if the exercise he did was actually what we classified or not. So we actually have labeled data. If we did it right, we know what was the right answer, and if we did it wrong, the user provides us the correct answer. We have labeled data, and we feed it to the batch layer, to Apache Spark, that can then use it to create better models. And although the preparation, the training of the model is computationally expensive, the model itself is actually just a couple of numbers. It's just a couple of attributes. So it can be serialized and sent back to the device and to Akka. And it can start using the new model actually almost immediately to improve user experience.
Absolutely. So more on the phone, right? Let's move to this sane world of mobile applications, just like Pebble. A whole bunch of code in C++. We want to have an Android and an iOS. Does anyone use Windows Phone? No, okay, good. All right, so core components in C++, again, multi-platform build. So this is where all the machine learning happens. Smallest possible device-only code, same development tools. So again, I don't really like Xcode, but you know, you're more than welcome to it if you like it. So here's an example. The signal processing has to happen on the phone. So one of the challenges was how to identify exercise from non-exercise. That turned out to be really tough. So when I'm just sort of walking around, do I even attempt to classify it? Or do I begin classifying only when I suspect I have something that might be an exercise? Turns out that I mean, look, I did some sort of engineering back in the past. So what do engineers do when presented with such a thing? Throw Fourier transform at it and go, that will give us our answer. And it does. So it turns out that if I'm doing something fairly rhythmical, fairly repetitive, then the distribution of the most powerful frequencies will coincide on all three axes very nicely, which is what we see here. So we generally go about doing this thing now is pick a high-level language, just try an experiment. You know, have some MATLAB code and have a Go or Octave if anyone wants to do it. Second problem was this. We padded with zeros. This was terrible. If only there were a way to somehow predict what a thing under acceleration might do. Well, there is, right? That's physics. So we already know how a thing, if I throw a ball, we know how it's going to fall. If I measure something against acceleration, I know the way it's going to move. We need to somehow predict things. So there are these zeros. We don't know. We'd like to know. Well, this is shamelessly borrowed from Wikipedia, but again, electrical engineers or engineers might think, oh, Kalman filter, that will do it. It's a way to eliminate noise and to give some sort of prediction. Now, we didn't write it by scratch. I mean, I'm too stupid to do this sort of thing. I can write C++, though, and use this wonderful Kalman filter class from OpenCV. It's brilliant, right? Just feed it the data. What we get is better, much better signal processing. More of the same, right? It all ends up being C++. And more. And we have this SAX classifier.
Yeah, so as we mentioned, we moved part of the machine learning pipeline from Akka to the mobile device, so into C++. This is an example of a machine learning pipeline that uses symbolic aggregate approximation as a pre-processing step, and then some kind of classifier. This is how, when we are pre-processing data, we want to reduce the dimensionality of the data, so to describe the same time series with less dimensions, with less data points. We want to reduce noise, but at the same time, we want to still be able to keep the important features, the important information in the time series. We still want to be able to describe it similarly. These are two examples using the very same pre-processing step, just with different parameters, and you can see it describes the time series very differently. And this is the reason why we actually use Apache Spark, so it can figure out the best combination of parameters where the model, where our machine learning pipeline performs the best.
Yeah, so you know, didn't mean to scare you really, but here's Xcode. But anyway, we just had to jump through a few hoops, you know, build this native library in C++. Same story, CMake, no problem. All the tests, all deliverable on some sort of CI and CD pipeline. And then some Swift headers through Objective-C++, and it still works. I mean, that's the great thing about it. And if you remember our device session, right sort of in the middle where we submitted the data to the server, well, what we do now is just push it back to our pre-classification pipeline and get the results right there on the phone with the current model. So hopefully that explains our new distributed Lambda pompous architecture with feedback, but it just is a splitting of the speed layer and realizing that the model needs to be updated perhaps on different machines and then sent back to the point that's closest to the census. So that's our entire application, and there's nothing more to it. It's all open source. It's all on GitHub. There's a whole bunch of code, and we'll be updating it with the latest experiments that we've done now. So you're more than welcome to clone it and have a go. Any questions?
Can you just give a brief summary of the main major differences between Akka and Spark?
Yeah. No,
Hello.
Yeah.
Hello.
Sorry.
Can you give a brief description of the main differences between Akka and Spark?
Do you want a slide? No.
Between Akka and Spark, they're actually quite different technologies. So Akka is on a different level of abstraction. So in Akka, it serves to help you build concurrent and distributed applications, but you have to do a lot of work yourself. You have to do the error handling yourself. You need to do the distribution. You need to do computation yourself. But in Spark, this is all done for you. So you just define the computation you want to do, but it takes care of how it distributes it to the cluster. It takes care of how to handle failures and so on. So it's like a different level of abstraction, and it depends what you actually want to do.
Any more? Yes, one more.
So where are you doing the test data set to train your exercise model?
Okay, the question was where do we get the test data set for our exercise model? First, it was our own lab testing. And then we have, as I said, we have a gym in the same building that our office is. So we sort of enrolled the first 100 users and we said, look, there you go, for free. What the user interface actually, when it comes to classification, particularly with the latest model, is if we classify the exercise, the watch will say, well done, you've done 10 of A. And then it also says on button, this one, it says, was it actually B? Was it actually C? So we get really, the main idea of this app, because of my laziness, was no interaction. Right? People just go in and exercise. They don't fiddle with buttons, enter stuff, unless they really have to. If they have to, it's click, click.
Yeah, so with this kind of feedback, the users themselves actually provide the data to us.
Okay, well, we don't want to keep you any longer. Thank you for your attention. One more thing. Yes. It's all there. And finally, if you have 6 months of time, read, unfortunately. I'll take this one.